polynomials, understanding in behavior turning points, which turning points turn into max and mins, localized or absolute. All right, so we're going to look at some examples. We're going to look at graphing them and, again, seeing kind of the behavior. Remember that leading term is what's vital. All right, so I've got two functions here. I've got f of x, which is a simple one-term polynomial. So f of x is negative 3x to the fourth. And then I have g of x. It's a little more complex, but its leading term is exactly the same as the f of x function. And I want to look at the behavior of it. So I'm going to look at the middle behavior, what's happening around the origin, the turning point kind of behavior, and compare it to the global, the big end behavior. All right, so turning points. And so I'm going to graph these two functions using a window. So again, these would be my x max and min. These would be my y max and min. So my x minimum is negative 5. My x max is positive 5. My y min is negative 20. My y max is 25. All right, so if I graph those, so this would be graph 1. This would be graph 2. So I graph them in the calculator. I'm just going to graph them and pop them up here. All right, so again, that window is what I get. So here's my x-axis, my y-axis. So again, this would be 25, negative 20. This would go out to negative 5, positive 5. So again, x, y. That's what it should look like. My x max is 25. My x min is negative 20. My y, and then that's my y's. My y's. My y max is 25. My y min is negative 20. My x max is 5. My x min is negative 5. All right, so then the first function. All right, the first function just is simply this. So that's a function that comes up, touches the origin, comes down. So there's the g of x, which is that negative 3x to the 4th. All right, it does hit the origin, so it is hitting there at 0, 0. All right, then the other function. Pick a different color to do the other function, so I'm going to do green. Oops. Oh man, so somehow I all the way down. There we go. All right. And so the other function comes up. Actually, a little lower than that, so it's like this. And there's f of x. All right. And so it does have 3 turning points. All right, so f of x has 2, so it's got 3 turning points, not 2. 3 turning points. G of x only has 1. Right? And so f of x has an absolute max. G of x has an absolute, so they both have absolute maxes. But f of x has some localized max and mins as well, where g of x does not. G of x only has so g of x only has the one absolute max. F of x has an absolute max, but it also has a localized min and a localized max as well. All right, and so this is what's happening in the middle, towards the origin, all right, toward the middle. Now we're going to blow it up. I'm going to graph it much bigger. And so I'm going to leave the same 2 functions in there, and what you're going to go do is you're going to change your window. All right, so again, what you're going to change is you're going to make your y minimum that negative 500,000, y maximum 100,000, your x minimum negative 20, x max positive 20. That's what this means. And now we're going to look at the end behavior. So before we were looking at the turning points, and they had very different. One of them only had 1 turning point. One of them had 3. Now they had the same extrema and the absolute, but they weren't the same locally. All right, now we're going to look at this. So if you blow this up and you zoom way out, the 2 graphs are almost indistinguishable from each other. All right, where did it go? All right, so if you look at it, they're basically, one of them looks like this, and then the other one looks like it's right on top. All right, when you blow them up, you can't tell the one from the other. All right, they look like they're almost identical. F of x looks almost the same as g of x. And when it comes to the end behavior, what's happening at the tails, they are the same. Right? As I plug in really big values, as I'm shooting off, my x values are going to infinity, my x values are going to negative infinity, and my function's doing the same thing. Right? The end behavior is as x shoots off to infinity, as x shoots off to negative infinity, well, my function's doing the same thing. My f of x or my y values are both shooting off to negative infinity, right? Both tails, both ends of my graph are shooting off to negative infinity. Right? In both directions. So when I plug in really big, and again, that should make sense. If I look at the leading term, which is the same for both functions, it's negative 4x, or negative 3x to the fourth. When I plug really big numbers into this, doesn't matter if they're positive or negative, when I take it to the fourth degree, they're going to come out bigger, right? So if I plug in 10, it's going to be 10 to the fourth, so it's going to be 100 or 10,000. If I plug in negative 10, since it's to the fourth, it's still going to come out 10,000. But I multiply by the negative coefficient out front, and so that's what's going to make all of my numbers come out negative. So they're going to get bigger because they're to the fourth power, so they're going to go off to infinity. And then because of the negative 3 out front, they get bigger times another 3, but they get bigger in the negative direction because I got a negative 3. And so that leading term basically tells me what's happening in the end behavior. Since it's an even degree, they're shooting off in the same direction. And since the leading term is a negative, they're shooting off in the negative direction. Let's look at the next another example. So this is an odd power. All right, so that was an even power case. So now we're going to look at the odd power case. So again, kind of the same thing. I'm going to graph these two functions, and you'll notice, so this will go in there as y1, this will go in there as y2. The leading terms are the same. G of x is more complicated, but its leading term is exactly the same as the simple function 2x. So odd power, 2 is a positive number, so keep that in mind when we go look at that. All right, so the first window, so these are my x values, these are my, so my first window, my x minimum is a negative 5, my x max is a positive 5. My second window is my y minimum is negative 100, y max is positive 100. All right, now we're going to kind of see the turning points, all right, the turning points on my graph. And so these functions actually, when I look at them near the origin, are very, very different looking near the origin. All right, so 5, negative 5 in the x direction, negative 100, positive 100 in the y direction. All right, so the first function, f of x, just simply looks like this. It goes through my origin. It's this S kind of shape. All right, so there's f of x, which is 2x to the fifth. Right. The other function's a lot messier. Now, it also goes through the origin, but then it's got a spot up here and a spot down here. It does have symmetry. Sorry about this. Apparently, when I hit that on the bottom, it scrolls me down. All right. There we go. So it does have symmetry. Flattens out there and then comes back up, and so there's my g of x function. So off the hand, g of x and f of x don't look anything like each other, right? F of x has no turning points, right? That's what we're supposed to look at. F of x, no turning points, no extrema. G of x has two turning points. G of x has two local extrema. It has two turning points. Local extrema. But however, it also has no absolute extrema. That's where they're the same. The absolutes are the same. Alright, the localized what can vary between my two functions. So the leading term can tell me if I have any absolutes or not. So you'll notice in these odd functions there's no absolutes because it's shooting off to infinity and negative. And the even function had one absolute. Right? So when I had odd degree, no absolutes. If you go look at the previous example, it was even degree, they had one absolute. Now, the more complex function has some local stuff, right? It's got a local max here and a local min there. So it's got two turning points and their localized extrema. But on the global, it doesn't. Alright, so that's what we're going to now zoom out. We're going to make it bigger and zoom out and see how that affects the graph. And so when we're zoomed in, they look very different. I'm going to zoom out and you're going to zoom out and see they're going to look pretty much the same. So it's the same window I used in the previous example. So again, these are my x values, these are my y values. So my x minimum is negative 20, my x maximum is positive 20, my y minimum is negative 500,000, my y maximum is positive 100,000. And so now when I sketch the graphs, I don't want to use red. And now they're going to be almost indistinguishable. So again, that would be 20, negative 20, that would be negative 500,000, 100,000. Alright, you'll notice they both go through the origin, and both of them look the same, right? If you graph these on your calculator, you'll see when you zoom out, even though we know some weird stuff was going on in the middle, right? By weird stuff, I mean this was happening in the middle of my g of x function. But when I zoom way out, I can't see that. All I can see is what's happening globally. Alright, what's happening when I plug really big numbers in, I get really big numbers out, and it's getting big numbers in both directions. So remember, the leading term was 2x to the fifth for both of them. Actually, 2x to the fifth was the one function, and that was the leading term. And so it's odd. Odd degree has opposite end behavior. When I plug in, so that means one side's going off to infinity and one side's going off to negative, right? This side's going off to infinity, this side's shoot. And that's the same for both the complex function and the simple power function. Alright, so the end behavior is the same. You can read that. The end behavior is the same. As I plug in really big x values, I get out really big y values. And it's the same. When I plug in positive, I get out positive. When I plug in big negative x values, I get out big negative y values. And it should make sense. Right? When I'm plugging in big positive numbers, it's going to stay positive because the 2 is a positive and odd keeps the positive. When I plug in negative numbers, it's going to go negative, right? If I take a negative number to an odd power, it stays negative. And since the 2 out front is just a positive 2, 2 times a negative is still negative. So, like things come out. I plug in big positive numbers, I get out big positive numbers. And so the end behavior is, as I plug in big x values, I get out big y values. As I plug in big negative x values, I get out big negative y values, right? And so this is the end behavior. And it's the same. That leading term is what tells me about my end behavior. All right, so that's the conclusion we're going to draw. All right, the leading term of my polynomial determines my end behavior. And that's where we're going to pick up the next video. All right, so it's the leading term. The odd degrees, the even degrees, and the number out front is what tells me how my end. And it also kind of can give me a clue on how many turning points I have, but we'll get to that later on. All right, so it's the end behavior that's telling me, it's the leading term that's telling me my end behavior.